Welcome to the second module where we're going to be looking at at language and mathematics. When we start this module, one of the misconceptions that people often have about language and mathematics is that mathematics is one of the curriculum areas that you don't need language in. And a common story you'll often hear is that students who come from overseas countries whose first language isn't English often can succeed in mathematics because they believe that mathematics is almost language free. However, in this session, I would like to dispel that myth and argue that language and mathematics are integral to each other, and then you can't do one without the other. So really there are three key ideas that we need to know. Pardon me. The first one is that mathematics is a language in and of itself. It has its own language, it has its own grammar, it has its own words, it has its own syntax, so in many ways it is a language. To give you another perspective on that, what often happens in many Western contexts is that the mathematics field of study often sits within the science area. So if you were studying maths at tertiary level, for example, you'd probably be located in the science faculty. Similarly, if you're in high schools, the maths teachers often work very closely with the science teachers. However, in many Scottish universities, this isn't the case, and in many Scottish universities, maths is actually in the language faculty in recognition of the unique language of mathematics. The other thing to consider is you can't learn mathematics in social isolation. You need to be talking with people, you need to be negotiating meaning. Maths is actually learnt through a social context, so it's learnt through a particular medium, which of course is language. You can't learn maths just by sitting in a space without other people, without other forms of linguistic interaction. We also know that maths is a spoken language. Maths is spoken, it's written, and it's also symbolic. So if we go back to last week, we talked a little bit about this when we were talking about communicating mathematically. Okay, so I want to give you a couple of examples of what it means in terms of language. So let's think about some of the examples you might get if you're going back to your secondary schooling, and I want to give these examples because they will get you to think. Often people assume that if you get something wrong in mathematics, it's a trick question. So here's an example that you probably encountered when you're probably in about grade 9 or maybe grade 10. So you've got the equation a plus b squared and you're asked to expand. Now, what does that actually mean? Here's an example of what some students would do. Expanding it a little bit more. So they've taken the literal meaning of expand and just spread the equation out. Now, hopefully you find that quite comical. I do. But what it means is there's a misconception about what that word expand means. In maths, that term expand has a particular meaning. Here's another example. Find x. So this is the typical Pythagorean problem. We've got 3, 4, and you've got to find the value of x, which is here. And what the student's done is circled it and said, here it is. And again, a misconception about the word find. We don't mean to look for and see it as we would in the everyday context. That word actually means to actually calculate, find the value of x. There's a lot of words that are redundant in there. The question's actually asking, find the value of x, not find x, as you would ask students to find something in a scavenger hunt. So these are the kind of things where we know that maths has a particular language. These questions are not trick questions. They are questions that have particular meanings within the maths context, and students get them wrong often because they don't understand the mathematical demands of that word. If we think about the early childhood context, because often if you give those examples, people say, oh, that doesn't apply to me because we're only going to be doing early childhood. A really common misconception with young children is when they're coming across even numbers and odd numbers, they'll often say they like the even numbers, they think they're good numbers. They don't like the odd numbers, they think they're bad, there's something wrong with them. Now, you've got to ask, why is that the case? And if you just look at those terms, even and odd, even could be an even-tempted person. That might be a little bit complex for a young child. But when you think about the word odd, odd has a lot of connotations in the worlds beyond school. And parents might talk about Aunt Flo being a little bit odd, a little bit weird, a little bit strange. So often those everyday meanings are then applied to the maths context. So we often hear students saying that, particularly the early years students, thinking that odd numbers are bad numbers or strange numbers or funny numbers. You also hear, here's some other terms that we often use, the term vulgar fractions. What does that mean? Well, vulgar has a particular context outside schools, and we use it in mathematics. And I'm sure, if you think back to when you encountered the whole notion of the square root, how much you giggled with that concept, because there was a word in there that was a little bit naughty to say, and then you hear the teacher saying it, and it is so common in classrooms, particularly in the high school context, where teachers will use square root, and it elicits a whole lot of giggles from the students. Another example is this notion of whole and whole. I've spent a lot of time working in remote Indigenous communities, and one of the words that we use a lot in mathematics is the term whole. Now, in many remote Indigenous contexts, the word whole is used to refer to a part of the woman's anatomy, and it's actually seen as quite a vulgar term to use, and in many communities it's frowned upon to actually refer to a whole, because it's talking about a woman's body part, which you can work out what that is. So it's very hard in those contexts to actually use the term whole, W-H-O-L-E, when we're talking about two halves make a whole, because the students are hearing you referring to women's genitalia. So the words that we use in mathematics have particular meaning in mathematics, but often the words are taken from context outside of mathematics and reapplied into the context of mathematics, so they become problematic for learning. So what we want to do now is talk about developing the language of mathematics. So the language that we have, it is important for developing the concepts themselves. We do know that language shapes our perceptions, and perceptions shape our language. So an English philosopher, Ludwig Wittgenstein, often talks about the notion of language games. And he talks about that concepts arise from the context within which we work. There's the Whorfian hypothesis, which you may have come across in other areas of your study. So for Inuit people, or some people will call them Eskimos, but the Inuit people have something like 32 different words to describe snow, because their life depends on being able to describe the conditions they live within. So that becomes very important. So with Wittgenstein, what he said, we've had to evolve, our language evolves because of a need. So for example, he talks about as for example, we were coming out of caves and we started to build our houses. If you think about it, like if you're the builder and you want to place blocks in certain areas of your wall, you need to have a language that will talk about the shape that you need, the size that you need, so that you can say to somebody, please get me a rectangular brick that's a bit bigger than this one or a bit smaller than that one. So the language of shape and size actually evolves from a particular context. Now this is just a metaphor, but it gives you a sense of how our language of mathematics is always evolving out of a need to be able to describe things. We also need, if you go back to our last topic when we talked about communicating and reasoning mathematically, children need to develop a language of mathematics so that they're able to talk about not only the concepts, but their thinking in terms of their logic, their reasoning, their justifications, their problem solving. So they need a language in which to describe what's going on in their head and their thinking. We do know that early childhood is a period of intense language development. So this is a very rich time for language to be developed. And if you think about areas of the early childhood context, the play corner, the block corner, and the rich language experiences that are in those places. So if you think about children building a wall or building towers, the language that they're using is they're talking about the shape of the blocks they're using, the position of the blocks on top, next to, near, beside, and so on, in front of, behind. This is a very intense period for children to learn many, many mathematical concepts and processes through that play context. We also know that many of the songs and stories that children experience in the early years of schooling also are critical to their language development. So for example, if you're talking about Goldilocks and the Three Bears, this food is too hot, this food is too cold, this chair is too big, this chair is too small, I need a smaller chair, a bigger chair, and so on. These are terms that the students are learning through a very informal play context, but they're integrating them into their repertoire of language. One of the things that we do know also is that in mathematics, many of the little words are very, very important. If you think about the term off and of, only the F is different. OF, OFF. 25% off is very different to 25% of. If I were paying for something, would I want to pay something that was 25% off $100, or would I prefer to pay 25% of $100? So these little words in mathematics are very important. However, we know from literacy is that when people are reading passages of text, the little words are often skipped because you can get the meaning of what's going on. In mathematics, that is not the case. So these little words become very, very important. What we also do know about language is that the children's background, where they come from, really influences their language development. So we do know, for example, the federal government now is investing very heavily in the early years of schooling, particularly for those students who traditionally and historically haven't been able to, for whatever reasons, access early childhood contexts, because we know that anything that we're investing in young children is actually going to help them as they come into school. So children from low SES backgrounds, for example, or children from Indigenous contexts, students from any background that is traditionally disadvantaged, will influence their language development. We do know, for example, and the work of Valerie Walker-Dean has been very poignant in this, is that the ways that mothers and children interact in their preschool years is very much around language. So we also know, for example, that low SES or working class parents are more likely to give declarative statements to their children, and middle class parents are more likely to ask rhetorical questions such as, would you like to do the dishes, as opposed to go and do the dishes. Middle class parents are more likely to say, would you like to go and get your red jumper, it's in the top shelf next to your blue trousers. Thinking about all of that language is very different from a low SES parent who will say, go and get your jumper. So those experiences are really influencing the language that the child brings to the school context. So when we think about mathematics, there's many levels of language to be learnt. At the very rudimentary level, there are the particular words that need to be learnt. So these are concepts such as square, rectangle, circle, and processes such as adding, subtracting, finding, those sorts of things that we're asking the children to do. There's a lot of comparative words, bigger, smaller, taller, shorter, those sorts of things. Now, again, in my work in remote Indigenous context, what we do know is that, for example, in the Anangu language, which is the Central Desert language, there is no language for comparisons. So if you want to say it's a long way, it's a longer way, or the longest way, the way they describe it is they would use an Anangu word, and it would be him go long way, him go long way, him go long way. So the intonation and the expansion of the word gives a sense of how long or how different those distances are, rather than using comparative words. So coming to school, those students need to know, and we need to teach explicitly, many of those concepts. Positional words are also very important. Next to beside, directional words, sequential words, and so on. So you can actually see that there are lots of words that need to be worked through and taught in many cases quite explicitly, particularly if we're looking at issues around equity. Similarly, there are everyday words, and these can be mathematical words as well. So if you think about a term such as volume, in mathematics, that actually is referring to the internal space of a three-dimensional object. But in the everyday language, it's more likely it can refer to the volume of a particular shape, or the capacity of the shape to hold something. But it also talks about the volume of the television, the sound magnitude. So there are many words that are used in mathematics that are taken from the everyday. They may mean the same, but they may also be very different. We also know that in mathematics, and we talked a little bit about this in the last module, is mathematics is a very symbolic language. Now, if you think about those two little parallel lines, we often say 1 + 2 makes 4. Well, does it really? Does that what that little sign means? Now, in the early years, we use those. We'll use a symbolic language in a way that makes sense to the child. So, 2 + 2 makes 4. But those two parallel lines, the equal sign, doesn't actually mean makes, because you could say that 0 + 0 makes 8 if you put the first 0 on the top and the bottom 0 on the bottom. That's actually incorrect. It does make 0 + 0 might make 8, but those two parallel lines actually mean equivalence. So what's on one side is equivalent to what is on the other. So 2 + 4 is equivalent to the two parallel lines to 3 + 3. They're the same on both sides. So we've got to be very careful about how we introduce some of our concepts. Or if we go the line of 2 + 2 makes 4, at some point in time, we have to make a transition from makes to equivalence. Similarly, in the maths language, there is a grammar, and the sentences the sentences are often very concrete and moving to the abstract. So if we think about mathematics, what actually happens is the mathematical terms, the mathematical expressions are the lexical density of those the language actually becomes tighter and tighter. So when you have that example of find x, what that actually means is it's lexically dense, because there are no redundant words in there. What we're saying is find the value of x, but we're leaving out the value of x. It is implied in the term find. So it's cracking the code of what that means. So let's have an example of what the lexical density was. In the early years, we might be giving an example. If Mary went to the shop and she bought 3 apples at the greengrocer's, and they were out of oranges, so she had to go to another shop to buy oranges. If Mary had 2 apples and 3 oranges, then she has 5 pieces of fruit in her basket altogether. So we have it around the story. We have the child creating images about 2 apples and 3 oranges, whatever they are, so that she's got 5 pieces of fruit altogether. The task in mathematics is more about making this far more symbolic and getting rid of the redundancy of all the stuff about shopping and baskets and fruit, so that the equation 2 + 3 = 5 can apply to Mary going shopping, and it can apply to how many dollars you might get by selling some items. So that equation 2 + 3 = 5 can be applied to many, many contexts, and that's what the goal of mathematics is to abstract the meaning in a very symbolic way. And in doing that, mathematics is a very lexically dense area, and that's where this confusion about problems being tricky arises from. They're not tricky, it's just they're lexically dense, and you have to understand the meanings behind what is 2, what is plus, what is 3, what is your equals, and what is 5. And if you know that, then you're able to do the mathematics. So there's different types of language that you also need to be aware of. There's the everyday language, where we have the same words in the everyday context, and they may have the same or similar meaning in the mathematics context. And there's many of these words. So the term base means the bottom of something. So the bottom of something, like base camp at Mount Kilimanjaro, means it's at the bottom, and the base on a triangle is the bottom line on the triangle. We also have words, they are the same words, but they have different meanings. So many of these are square. A square is a particular shape in mathematics. In the outside world, a square can be somebody who's a bit of a boring person, so on. And there's some of those examples there. But we also have in mathematics, the term time often can mean different things in different contexts. So we could be referring to the passage of time using clocks, or, and this is quite incorrect, is when we're using the multiplication facts. It's in that incorrect use of the term, but we still do it, rightly or wrongly. Then we have words that have the same homophones. These are words that have the same sound, but they have a different meaning, such as whole and whole. So when you see the word written, the confusion won't be there, because you can see it's a different word. But if you think about, if you have two halves, they make a whole. If you're giving that context in a lesson of donuts, with a donut which has a hole in the middle, can you imagine the confusion that creates for a child when you say a half plus a half makes a whole? That children can hear whole as in being one whole unit, or it could be the hole in the donut. So we have to be very careful about homophones. And then there's the unique mathematical language itself. So these are terms that we only use in mathematics, and very rarely used outside of mathematics. So words like symmetry, tessellations, numerator, denominator, and so on. So these are terms that the students need to know about mathematics. And finally, the other part of language that I've alluded to at the start of this module was that we need to think about mathematics and inclusion. So mathematics is a language of its own, and students need to access that language if they are to become empowered. But as a teacher, you need to be aware of how language may be including or excluding your students. So there's examples in that previous sections of how you may go about that. Now, one of the most salient terms that we use in mathematics, particularly in the early years, are the terms more and less. So which number is 2 more than 3, which number is 3 less, which number is more, 2 or 3, which number is less. And we use these terms significantly in early number work and early measurement work. And we use it as unproblematic. There now is a corpus of research that says that middle-class English-speaking parents will use the terms more and less in their everyday interactions with their children. However, students from low SES or working class families, or students whose parents don't have English as their first language, or students from Indigenous backgrounds very rarely use the term less in their home language. So parents are more likely to say, would you like more ice cream, or do you want not so much ice cream? So the term less is missing in the home vocabulary, or it's not heard often. So when those students come into our classrooms and we're doing all of this extensive number work, essentially they're probably missing half of what you're teaching, because they don't access what you're talking about when you're talking about less. So this is an area that you really do need to focus on in your own teaching. A little word with significant impact in terms of students' access to mathematics. So hopefully you've got a bit of an idea now about the importance of language in mathematics, and that mathematics is not language free.